Okay, so I'm Ora, and I'm here to talk about symbolic AI. And this may be sort of a strange topic now that everybody wants to do generative AI, but I promise you it's something that everybody needs to understand and learn about if you don't already. So a few words about me. Since of my misspent youth, I have a PhD in AI and CS. Was involved in creating the original vision for the so-called semantic web. Was co-author of the original RDF specification. If you don't know what RDF is, I will tell you. I'm also author of this book, and fun fact, my software flew to the asteroid belt at some point. And it was symbolic AI, and I will mention those technologies in a minute. So this is kind of my game plan today. I'll give a very brief history of AI, the part of AI that spans more than 3 years, like everybody thinks, and I'll talk about what are the elements of symbolic AI. And then I'll talk about what is symbolic AI today and why is it relevant and what are the useful technologies that you can apply today. And then I'll conclude with a little bit of discussion on what this means from the standpoint of non-symbolic AI, generative AI, all that new stuff, so to speak. All right, so when I originally wrote this talk, I had a much bigger section on history, but the overlords didn't want that, so I'll just give you a very brief introduction. So this is basically the history of AI. What's important to understand is that it spans more than 80 years, and it's sort of a pattern of excitement and disappointment. We are currently in the middle of the third AI summer. We call these summers and winters. And I have been sort of a little bit of a skeptic maybe of the new AI, and because I don't want to see a third AI winter. I lived through the second one, and I continued to work on AI, and people were downright hostile, saying, "Why are you doing this? AI is the stuff that doesn't work." But here we are. So, symbolic AI, or as it was originally called, just AI, is a collection of all kinds of technologies, and this is my incomplete list, but I think it's a representative list in the sense that these are the important core technologies in symbolic AI. Now, of course, it's important to understand that the history of symbolic AI also includes successful deployment of systems that made use of these technologies. So it wasn't all just research or anything. And I won't talk about all of these. I simply won't have time. We would be here all day. But you can come and talk to me afterwards if you're particularly curious about something, and I'm happy to talk at any length about any of this. What's another thing that's really important to understand about the history of AI is that we have this pattern where some technology comes about. We think it's AI. Then later on we learn what it's actually about. We understand it. And then we go like, well, that can't possibly be AI because I understand how it works. And so many of these constituent technologies from the past have sort of stopped being AI. They are just mainstream. I mean, rule-based system, nobody thinks of that as AI anymore. Heuristic search, certainly nobody thinks of that as AI, but they very much were AI around the time when they were conceived. And then at the bottom here, what came from the long span of AI research were two new programming languages. And okay, so now you think, ho-hum, programming languages come about all the time. But this is not just languages. These were two completely new programming paradigms, functional programming and logic programming, that originated within AI research. And now we don't really think of them as AI anymore. Okay, so throughout this talk, I will have to talk about things like symbolic reasoning, logical reasoning. So I'll give you just a very quick introduction to that. So here's Wally. Wally's a good boy. We can represent, so in symbolic reasoning, we use mathematical logic and set theory as a sort of representational language. And so we can represent all dogs as a set, let's call it dogs. And then we can say that Wally is a member of this set, which is one way of saying that Wally is a dog. And so now, let me sort of demonstrate a simple kind of inference rule, how we can do symbolic reasoning. So first, let's say we want something where X belongs to a set, and let's call that set C. And then we also say that C is a subset of D. And if those things hold, then we can conclude that X is actually also a member of this larger set D. And this is an inference rule. So now, if we say dogs are a subset of mammals, and we know that Wally belongs to dogs, then we can conclude that Wally also belongs to the set mammals. Wally is a mammal, so to speak. Now this, of course, sounds incredibly trivial, right? But symbolic reasoning is like that, and real-world applications of symbolic reasoning are far more complex than this. But the principle still is the same. So here's just a visual representation. There's a set of dogs, and Wally is there, and then there's the larger set of mammals. Okay, so now everybody understands what symbolic reasoning is. Yes? Nothing? Okay, excellent. Good. So now we can move on. So let me talk about knowledge graphs and ontologies. Because those are really the prominent manifestation of symbolic AI today. And in a way, sort of, they are that because about 25 years ago, there was like a sort of a resurgence of symbolic AI techniques that brought about this. So a couple of terms first. A graph, and when we talk about graphs, we mean the mathematical notion of a graph. So it's a structure of nodes and edges. Typically, if you want to draw this on your whiteboard, it would be circles and arrows between them. But we don't mean a graph in a graphical sense. And a knowledge graph is an application of a graph where basically the nodes represent or denote some real-world entities. And the edges then represent various kinds of relationships between these entities. So we can use knowledge graphs to link information and organize information. And this thing that came about 25 years ago, the semantic web, knowledge graphs today are really the modern manifestation of that idea. The primary purpose for knowledge graph is really to capture knowledge and oftentimes in a sort of collaborative organizational context. But there are other uses, very good uses of the same technology. So something that I've seen many times and also built systems myself. So just make knowledge accessible to people and more recently to LLMs also. A sort of a low-level feature of knowledge graphs, it all comes almost like a sort of a bonus benefit, is that they're very good for data integration. You can take your whatever data you have, we'll call that legacy data, and you can map it to a knowledge graph. And if you do this right, the knowledge graph will represent the integration of these different data sources. And then finally, there's something called digital twins. People build these. They are really sort of a complex representations of physical systems in a digital form. And so we could imagine like a digital twin of an electrical system, and then you could use that to ask questions like, okay, if I throw this switch, what happens? Or if this circuit breaker blows, who's affected? So to build a knowledge graph, you have to have a model of what the information is in your knowledge graph, and this model is called an ontology. And I will come back to that, what that means. Now, when you finally build this knowledge graph, you have to store it somewhere. You have to be able to manipulate it. And for that, you need a graph database. And just as a purely random example, Amazon Neptune is such a graph database, and a highly scalable one at that. So let's talk a little bit about what an ontology is. So there is a common definition of what an ontology is, and if you look it up, you always get the same definition, and it's completely useless. So I won't even repeat it here. This is my definition of what an ontology is. So ontology consists, first of all, of concepts that you have identified. You can think of them like classes. So to follow our example, a dog would be one of these concepts. And then you define properties for these concepts. So in case of a dog, that might be fur color, for example. You also define relationships between instances of these concepts. So dog typically has an owner, and that owner typically is a human. You may specify logical constraints that have to hold. So my example here is that dog and cat, the intersection of dog and cat is empty, which means that if you think of these as sets, these sets they don't have an intersection, they are disjoint. And then finally, and this is not every ontology, but ontologies sometimes may also contain actual individuals, as we call them. So Wally would be an individual. Wally would be an instance of the class dog, if you want to think about it that way. To define an ontology, you need an ontology language. And what we didn't have back in the 90s, what we do now is we have standardized ontology languages. And I'll come back to talk a little more about what these standardized ontology languages are. But it has really made use of all this stuff a lot easier because we have standards. That means people can build tooling and all that. So I mentioned that ontology is something that captures the semantics of a domain. So what is semantics really? I mean, anyone use the word semantics? Yeah, I think people use it a lot. Most people don't know what it means. I find that just a tad ironic, because semantics is really about meaning, and I think of semantics in a sort of slightly informal way, that it's really definitions of how some piece of software can interpret your data. And so given that, semantics comes from the relationship that your data has with whatever definitions you have in your ontology. Ontologies are the means to kind of capture the semantics and convey those. But it can also come from the relationship between two pieces of data, that they have some kind of relationship, and that gives them meaning. So for example, two humans, and we say that this person is the child of that, we might be able to conclude that other person is a parent And then things that you can't express this way, then of course you have to hardwire the semantics in code. And historically, of course, all semantics was hardwired in code. And the great aspiration is that we can move towards a situation where things are more definition and data driven and not so much buried in some black box that cannot be really inspected so easily. The interesting thing about semantics is that people typically have a very hard time making the distinction between formal semantics and their own interpretation of some data, for example. And this matters because it creates unrealistic expectations of what software systems can actually do. And as a result, I often hear this, people say, JSON is easy to understand. Who here thinks JSON is easy to understand? Well, some people, okay. Not everybody, that's good, okay. So I'll give an example, what I mean. So here's a little snippet of JSON. I'll give you a moment to look at it. When you read it, you think, yep, okay, I understand what this is. I understand the meaning of this data. This is a very sort of a human reaction. I'll give you another snippet of JSON that ostensibly has exactly the same meaning. And you tell me if you still understand what it means. Maybe somebody here actually speaks Finnish, and therefore you can interpret that the same way you interpreted the previous one. But I think of Finnish as sort of as a language, it's sort of like a weak crypto mode. The key is known, but very few people have it. Anyway, this is the same thing. I just translated the keys and some of the values to Finnish. And in the English version, you basically performed a grounding of these symbols. Grounding of symbols like degree or hobbies. You interpreted what that is based on your experience and your understanding of English language. And now you think that that's the meaning. Of course, I could say that this data means something completely different and has no relation to the English words that are there. But what you see here is how data looks like to all machines all the time. And so I don't think JSON is easy to understand. All right, so that's kind of still background. Now I'll talk a little bit about what it means to work with ontologies. And so let's say you decided you need a knowledge graph, and therefore you need to have an ontology. So the first question is really the sort of build or buy. And when I say buy, I don't really mean literally buy, because ontologies tend not to be for sale. They tend to be shared. They tend to be public, but same difference. So your choices really are, first of all, you could just find some ontology and go like, okay, this is perfect for my use case. I will just use it as it is. You have to assess the suitability very carefully. And I'll talk a little bit about what this assessment actually is. It will be helpful when you start choosing ontologies. You could take that existing ontology and go like, yeah, it's almost what I need, but not quite. So I'm going to be extending it. And ontology languages have been designed in such a way that it's possible to take an existing ontology and extend that for your own purposes. There are also a thing called upper ontologies, which can be a good starting point for this kind of an exercise. What's important to understand is that every ontology, or the designer of that ontology, has made some decisions about how to model the world. And you have to understand what these decisions are. Otherwise, bad things could happen. Now, the third option is that you'll start from scratch, go like, okay, I don't need what others have done, I'll just define my own. That's perfectly fine. Just prepare to do some work. Because, and lately I've heard a lot of people say, oh, I'll just let the LLM write me an ontology. An LLM can write you an initial draft of an ontology, but after that, it really requires human eyeballs. All right, so let's now say you found an ontology, you're thinking maybe I'll extend this, but I have to first assess the suitability. So what is that? First of all, consider your use cases. Not necessarily one use case. Pick a couple of use cases and be prepared to find more use cases in the future. The knowledge graphs have this interesting characteristic that you build something and you think, okay, this covers my use cases, and then you realize, oh goodness, this knowledge graph can answer questions that I didn't anticipate. And then you may have more use cases and uses for that knowledge graph. When we design an ontology, we usually define what is called competency questions. So these are really questions you anticipate that if you do this right, your resulting knowledge graph should be able to answer. So in some ways, the competency question should be translatable to graph queries at some point. And then coverage means that you have something you want to model. You look at your enterprise or your organization and go like, okay, we deal with these kinds of concepts. Make sure those concepts exist in the ontology that you're going to use. And if they don't, extend the ontology to cover everything. So that's one. Then there's this question that I mentioned that people have already made decisions about how to model the world. I call these ontological commitments. And this is where what I like to call the law of unintended consequences comes to play. So it's like, in other words, it's this seemed like a good idea at the time. So you take this ontology and later on you realize, oh goodness, I can't do certain things because some decisions that were made way earlier, that happens all the time. And then finally, there is a question of expressive power. So expressive power is really a measure of what are the things you can say using your ontology. And so for that you need something called a reasoner, typically. And you will always have this sort of a trade-off between expressive power and the computational burden for using a particular ontology that requires that particular level of expressive power. The more expressive, also more difficult to compute, generally speaking, as a sort of a gross generalization. So what can you use these things for then? So a very typical use for ontologies is that you can operationalize or automate the processing of your data. You basically have data and have sort of the meaning, the semantics of that data, follow that data. And the aspirational end goal is that you can have software that can process that data, can interpret that data in some ways, without actually that having been coded in there. You just give it the ontology, and it interprets the ontology and can do meaningful things for that data. And that's a real thing, that can be done. Ontologies can also be used to uncover implicit information. So that whole example where Wally is a dog, and now we find out, oh, Wally is also a mammal. We never said that Wally was a mammal. We uncovered that. That was implicit in the data. Ontologies can serve us as documentation. And having said all these things, and there's a lot of sharing here, at least to me, the implication is that I really would like to stay away from closed proprietary ontologies. They can certainly solve certain problems, but they don't give you the full benefit of what ontologies can do. All right, so some examples of shared public ontologies that you can use. So first of all, there are these upper ontologies that you can start from. Basic formal ontology is very, very abstract, and I always feel like you really need like a graduate degree in philosophy to use it. Gist is a much more practical one. Both are popular. Then we have domain-specific ontologies. FIBO is about the financial industry and all the different concepts in the financial industry. SNOMED is a medical thing, and SciDoc is an ontology for people who want to capture cultural heritage, museums, archives, what have you. Now, in addition to these two categories, we also have these kind of narrow ontologies for like single purpose that you can mix into your own definitions. These are the four of my favorites. Dublin Core has been around for a long time. Provo is an excellent model for capturing provenance. And I will later have an example of what SCOS does sort of when you build taxonomies and thesauri. So let's build a quick ontology and see how that works. So and this uses RDF and OWL as the ontology languages, and it uses a particular syntax of RDF called turtle. RDF has multiple syntaxes depending on your preferences. So we define a class called dog. We say it's a subclass of, first of all, mammal, and also a subclass of pet. And then we say it's disjoint with cat. Okay, so this is in line with what we talked about earlier. Then we define a few more classes: cat, human, mammal, pet. Pretty clear stuff. And then let's define a couple of. Let's define one property, the fur color property, and we say fur color property is something that belongs to dogs, and the value is some string. We don't say what that string can contain. An owner is a relationship that links pets and humans. So this is our simple ontology. In knowledge representation, we would call this a T-box or terminology box. These are the definitions of your data. Then we also typically have this another thing called a box or assertions box, which is really the instantiations of those definitions. So we say Wally is a dog, white and black fur, has an owner, Coco is another dog, Ora is a human, things like that. Those are individuals, and those don't have to be part of your ontology, but they will go into your knowledge graph. And because we're using RDF, we have a graph representation of this. So here it is. Wally is an instance of the class dog. Ora is an instance of a class human. And Wally has an owner called Ora. So simple graph structure. But RDF has this kind of self-similar structure. So we can actually include the definitions themselves in the graph as well. So in this case, dog and human would both be instances of a class called class, which now would be sort of a meta class, obviously. And here's an example of me querying the data that we saw earlier using Neptune. We have extended the Jupyter Notebook so that you can run queries directly from cells and get the results, and those results can be tabular or they can be visualized as a graph. So all this is, what I'm talking about is absolutely real. And when you want to start building a knowledge graph, we can help you. All right, so I mentioned that there are different ontology languages. So first of all, RDF is a very simple ontology language. Here are some examples. I define pet, and I define the owner relationship. And then we can use that to infer new data. So if I say that owner is a relationship that links pets and humans, and then I say that Wally, who is a dog, and we know dogs are pets, has an owner called Ora, but I haven't said anything else about Ora. we can infer that Ora must be a human. Now, OWL is a more expressive ontology language, and we can express restrictions using the subclass mechanism. So here we say that a pet must have exactly one owner, and that owner must be a human. And if we then take an OWL reasoner and we take your graph, if there are unsatisfied restrictions, two possible things can happen. Either the reasoner reports that there are inconsistencies, or it will add new information to your graph to make it so that those restrictions are satisfied. So similarly, it could infer that the owner, if I introduce an owner but it's not a human, the reasoner could actually infer that the owner actually is a human. Shackle is a language, RDF-based language that was originally designed for validating your RDF data. But you can use it to express constraints. Those constraints in Shackle are called shapes. But unlike RDF and OWL, Shackle never infers new data. So if there are unsatisfied constraints, your Shackle engine will simply tell you that your data did not validate. So why is this? Why do RDF and OWL work differently from Shackle? So we have to talk about something called world assumptions. So first of all, closed world assumption is this thing that we assume that what's in your database is all that there is. There is nothing else. And so whatever reasoning you do can be based on the fact that you have complete knowledge. And that means that you can use something called negation by failure. So if you can't prove something to be true, you have to conclude that it's false. Traditional databases tend to use the closed world assumption. Open world assumption, on the other hand, is the idea that we don't know everything. There could be more information out there, and we can't possibly assume that we have it all. So that means you can't use negation by failure as an inference rule. We adopted this for the semantic web because we thought, well, you know, the web, maybe you haven't reached that particular server, you hadn't collected that particular piece of data. There could be more stuff, so made perfect sense. And now just a quick word about those ontological commitments or modeling commitments. So we defined that pet can have only one owner. But what if there's like joint ownership of some pet? How do you do that? So this is a very common occurrence. You pick an ontology, you do modeling, later you find out, oops, can't do that. So possible solutions, if you control those upper definitions, you can just go and refactor your code a little bit, the code of the ontology that is, and make it so that there can be multiple owners. Or you can introduce a new relationship, co-owner or something like that. There are ways to fix this. And then when you define your ontology and you have different kinds of concepts, sometimes you have concepts that are really variations of one another, and you can capture this using a class hierarchy. The alternative is to capture these variations using something we call concept schemes, and I'll explain this. So let's say we want to represent dogs in such a way that we also capture the breed of a dog. Okay, so here's some definitions. Dog is a class. Toy dog is a subclass of dog. Shih Tzu is a subclass of toy dog. And these are the, I don't know, American Kennel Club classifications of things. You know, we introduce all these definitions, and now we say that Wally is a Shih Tzu and a poodle. These are called designer breeds nowadays. I would call them mutts, but But anyway, here we use the class hierarchy to do that, and it sort of looks like this. Note that we can have instances that are instances of multiple classes. So multiple inheritance in RDF that is not limited to classes alone. If you don't like that, you can introduce that designer breed, which in this case is actually called Shipu, real thing. And then you can just say Shipu is a subclass of both Shih Tzu and a Poodle, and then Wally is an instance of this class. All good. Now the alternative is to say all dogs are really much alike. I don't want multiple classes. I don't want to clutter my ontology with a large number of classes. So let's put a property on dogs called breed, and then decide what kind of values can that property take. And for that we need that SCOS vocabulary that I mentioned earlier, and we build something that's called a concept scheme. And we define all these things that we earlier defined as classes, we now define them as SCOS concepts. And then we can just say that Wally is a dog and Wally's breed is Shih Tzu and Poodle. But basically you represented the same stuff. It's just that you only have one class now. And again here, if you only want the breed to have one value, you can again introduce the designer breed as a separate concept and then do this. So this is how it works. This is how you define ontologies and work with the classes and the definitions. So a couple of quick words about how to actually work with reasoning. And this does not require a PhD in math. You can do this. I mean, maybe some of you do have a PhD in math, that's fine, but it's not a requisite here. So there are many use cases for reasoning. One is this, what we already talked about, uncover implicit information. We say Wally is a sheepu, we can conclude that Wally is a dog, we can also conclude that Wally is a mammal. Those can be handy things to know. We can discover inconsistencies. If I say Wally is a cat and a dog, the owl reasoner will tell me that you have a fundamental inconsistency, one that cannot be fixed by adding more data to the graph. Reasoning can also be used to make query authoring easier, because you can operate, let's say, just using the base classes, for example. And your ontology can evolve, but the reasoning basically insulates your queries from the changes in the ontology. You can add more dog breeds, and this query will still work. RDF basically more or less just gives you taxonomical reasoning. But in addition to class hierarchies, also properties can have hierarchies, which is a very handy feature when you are extending somebody else's ontology. You can introduce your own properties, but you can say, well, these are really extensions of those properties that came from that other ontology. So here I have defined an owl class called Black Poodle. And I have defined it in a way where I say breed must have the value poodle, and fur color must have the value black. Now earlier I said that we use subclassing to introduce restrictions, but here I've used something called equivalent class. And the difference is this. If you use subclass, that introduces a necessary condition. All black poodles must satisfy those constraints. But if you use equivalent class, it's necessary and sufficient condition, which means that if you find something, or the reasoner finds something, where breed is poodle and fur color is black, it can actually conclude that this is an instance of the class black poodle, which means that the reasoner can be used for classifying your data. Well, now, of course, there's the question of how and when to do this. Some triple stores or graph databases for RDF, they have a built-in reasoner. If not, there are options. You can even use Sparkle, the query language, as sort of a reasoning engine. Here's an example of figuring out what the class of an instance is. Without reasoning, you can rewrite your query to basically climb the hierarchies in the ontology and do the same thing that a real reasoner would do. This happens at query time. If you want to do this before querying, you can materialize these results of the reasoning beforehand. Results of reasoning, by the way, are called entailments. You will see this word pop up every now and then. If I say entailment, think about results of reasoning. So this would be a way to kind of materialize the entailments in your graph. And there is a choice between these two. Do it query time or do it beforehand. If your data changes a lot, it may be more useful to do it at query time. But if your data is more or less static, you can do it up front, and then you don't have to do anything when you're querying. So when you're materializing, you will encounter this problem that we call truth maintenance. I used to think that truth maintenance could be like something an authoritarian government does. But it turns out that truth maintenance is the question of, okay, I've materialized some entailments, and now I've changed the data. Which entailments do I have to retract now? Because they're no longer supported by the original data. And this can be a very costly operation. If you use Sparkle, the query language, as your reasoning engine, you can do this, what I think of as poor man's truth maintenance. You materialize, you put them in a separate named graph in your, RDF has this feature called named graphs. And then you can drop that graph and recompute when things have changed. All right, so that's that. Now a few words about the new AI and its relationship to the old AI, so to speak. So can the old AI help the new AI is really the question. All of you must have seen this quote. What's important about this thing is that Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. He didn't say it is magic. And there are a lot of people who think of the new AI as sort of magic, but it isn't magic, and it's really important to keep that in mind. So we have some challenges. We all know that these are challenges. So hallucinations, obviously. LLMs will make stuff up. And that's a feature. They're supposed to do that. But it makes it difficult to build systems. Anthropomorphism. People start thinking of their chatbot as an actual human. And the answers sound convincing. People will believe them. They won't check them. This is a problem. And then the computational efficiency is definitely a problem in the sense that if you already know how to compute something, then just compute it. Don't ask the LLM because it's highly inefficient. And our energy supply is finite. Related to this are some interesting historical criticisms of AI. Joseph Weizenbaum in the 1960s built what is the first chatbot. And it was very crude, obviously, compared to what we have today. Use sort of these rules and pattern matching. But he noticed that people started having conversations with this chatbot as if it was a real person. And it turned Weizenbaum into a vocal critic of AI. He didn't like the idea of anthropomorphizing computers. The Chinese room experiment is an interesting sort of philosophical question that really asks what is consciousness and what is understanding? Can machines understand something? Can an artificial system be conscious? I used to think it's only a philosophical question, but lately, maybe it's a more practical question even. These are highly relevant today. The history of AI is about scarcity. We always had scarcity of something. We didn't have the right algorithms. We didn't have enough memory. We didn't have fast enough processor. Those are more or less solved in many ways. We have enough of those. But we have other scarcities today. And this is my list of the scarcities we encounter today. So let's talk about these a little bit. We want correct answers, right? We don't want the system to hallucinate some bullshit. So you could pull the answer from a knowledge graph rather than have the LLM produce the answer for you. Accountability, trustworthiness, same thing. You want to know where the answers are coming from. If they come from your knowledge graph, that knowledge graph can be curated and audited, and you can make sure that it contains provably factual information. You want to be able to explain the answers. An insurance company will tell a policyholder that their claim was denied. I'm sure the first question that the policyholder has is, why was it denied? You want an explanation. And explainability is a prominent feature of symbolic reasoning. When you do symbolic reasoning, you can always trace back why you got the answer you have. And then this energy question. So getting an answer from a knowledge graph for a question is literally several orders of magnitude more efficient than getting it from an LLM. So there's a growing understanding that the future AI systems really are going to be hybrid. They will combine different kinds of technologies, symbolic and these newer non-symbolic techniques. But in cognitive science, there's been this idea of what they call dual process models of cognition. This is an idea that really was popularized by Daniel Kahneman's book, Thinking Fast and Slow. It wasn't his idea originally, but he made it popular. And the idea that there's a fast process that gives you an answer right away, but that answer may be incorrect or biased or something. Or the answer can also be deliberated a little more, and you get a more trustworthy answer. And there was also in the 70s, there was a lot of interesting work where people really started thinking about intelligence and consciousness and started drawing like what we now would think are like architecture diagrams, software architecture diagrams. Aaron Sloman, Daniel Dennett did a lot of work like that. So here's my sort of very trivialized idea of how to use an LLM with a knowledge graph. Ask a question, the LLM translates the question into a query. The query runs, answer comes from your knowledge graph. And of course, not just basic query processing, it could include symbolic reasoning as well. Now, how does this fast and slow thing work with this? So it could be something like this. LLM gives you a quick answer, or you go the other route, you get a more sort of effortful answer. Other architectures, of course, are possible and make perfect sense, but I like this as sort of a simple explanation of what these things might look like. So now you're going to ask, well, this is GraphRag, right? This is not GraphRag. So GraphRag uses a graph, not necessarily a knowledge graph, to basically improve the LLM performance, accuracy, whatever. But I'd like to kind of flip this and use an LLM to improve the performance and usability of knowledge graphs. And now with LLMs, we finally have a decent natural language capability. And so taking questions, translating them into something, but having the answers come from a knowledge graph, to me sounds like a great idea. And then finally, people talk about neurosymbolic AI. So let me explain what that is. So symbolic AI is often seen as kind of unrealistic and too idealistic. Everything has to be perfect for things to work. Now, on the other hand, on the positive side, the representations are completely transparent and results can be explained. Non-symbolic idea, on the other hand, while it can deal with the sort of messy real-world data, the representations are opaque, you can't really look at them, and the results cannot be explained. So what we would really like is to get all the green stuff, right? So here are some examples of what neurosymbolic AI could be. It is not a single architecture or methodology even. There are many different ways to combine symbolic and non-symbolic processing. So combining the two could be that you have used a heuristic search, but your evaluation function in the search is actually does some neural processing, for example. And obviously this System 1 and System 2 architecture is an example of that too. You could take non-symbolic input, like a picture, photograph, convert that to some symbolic representation, and then use symbolic techniques to reason from that symbolic representation. Or you could take symbolic data, but use that with a non-symbolic, like machine learning, some machine learning algorithm, for example. People have done work on like showing how mathematical equations can be simplified, and then fed those as training data to a machine learning system, and come up with a system where they claim that, well, now I have a machine learning system that can do mathematical simplification. Now that's still guessing, but results have been remarkably good. All right. So I suppose I should summarize a little bit. I hope you're going to take some of this with you. So AI has been around for a long time, longer than 3 years, okay? And there have been many useful techniques and technologies developed over this period of 80 years or something. And these technologies, once they're well understood, they really stop being AI. Now, in the early 2000s, we saw this dramatic shift from symbolic to non-symbolic AI. But the symbolic AI techniques are still relevant. And ontologies, you can do this. You can use ontologies. You can build knowledge graphs. You can operationalize your processing of your data. You can document your data better using an ontology. And you can even use reasoning. This is all quite real. And then finally, we can mitigate some of the problems that we have with LLMs using symbolic techniques. Not only ontologies and knowledge graphs, mind you, like planning and autonomous agents that come from symbolic AI. Those techniques can be very useful. We didn't have time to talk about that, but I'll hang out here. You can come and ask me if you're really interested. The whole idea of planning particularly is something that the modern manifestation of agents tend not to do, and I always think that agents have to be able to do planning in order to exhibit autonomy. We'll see many more of these hybrid systems going forward. We have a little bit of time. I'm not going to answer questions now, but come talk to me afterwards. It's much easier to answer questions that way. So thank you very much. And if you later on have questions, you can always email me, remind me of this lecture, and my email, so I'm Ora, and my email is super difficult to remember. It's ora@amazon.com. And thank you so much.